In this video, we're going to go through how you would draw head diagrams for a one-dimensional vertical column with a type 2 boundary at the top and a type 1 at the bottom. In addition, we're going to review how the flow changes as a function of time into and out of this column. We have a 100 centimeter long vertical column. It's experiencing steady state downward flow. The initial condition here is going to be that the pressure head at the top of the column is 0 centimeters and at the bottom is 100 centimeters. And we saw this before. That was a hydrostatic condition. So we can imagine that we have no water that's pouring into the column to begin with. And then at some time, we're going to change the condition so that we have a transition to a new steady state. This new condition has a higher pressure head at the top of the column, and overall this is driving downward flow. So we're considering an instantaneous change from the initial white condition to the final green condition. And we're going to think about this as a change that takes place at the top boundary and then propagates through the entire system. The question is, how do the pressure head and hydraulic head transition between these states? And the answer, as with almost everything, is that it depends. In this case, it depends on the type of boundary condition that we apply at the top, whether it's a type 1 constant head or a type 2 constant flux. Let's start by considering a type 2 boundary condition. That's what we saw in the movie, where we instantly changed the inflow from one lower rate to a higher rate. The key is, how do we translate this physical boundary change, the changing of the rate that water is being applied, into something that makes sense in terms of the flow equation, so something that makes sense in terms of hydraulic head. And here we have to recognize that the constant flow or the defined flow boundary condition is really a defined gradient in the hydraulic head. If we know K and we know the gradient, then through Darcy's law we know the flow. Or if we know the flow and we know K, we know the gradient. So what we can do then is to imagine at some point in time when the water level has raised to some height, the hydraulic head at that boundary will be higher than the initial, but it won't quite have reached the final. And what we know at that point is that the gradient coming into the domain is the same as the final gradient, because we have instantly changed to that flow in. So this is where we start. We start drawing this line with the gradient that is equal to the final, and then it has to transition until it is the same as the initial. So in other words, beneath some depth, the column won't yet have experienced the change that was applied on the top boundary. So this is this transient region where we have the final condition established at the top in terms of the gradient, if not the head, and we have this smooth transition to the initial condition beneath some point. Let's break this down in some detail. Up near the top boundary, we have the incoming flux, the gradient that's applied at the boundary, and then at some depth we can imagine that the gradient has decreased because it's continually decreasing towards the initial gradient, in our case 0 vertical gradient. So if we look right at that location where we have that change in slope, then we can imagine that if the K is the same, we must have more flow coming into the medium at that height than we have going out of the medium at that height. So from the flow equation then, if we have a divergence of the flux, more flux in than flow out, we must have a change in storage, and in this case an increase in storage. This continues throughout the column with ever decreasing gradient until we reach the bottom of the column where we are at the initial gradient. Looking at this depth, remember we have more flow coming in than we have going out at that time. So more water is going into storage, and the way that's accommodated is that the pressure increases. Therefore the water density increases very slightly and the porosity increases. So we can imagine that at some later time that location would actually experience a higher pressure. Similar pressure increases occur throughout the profile, leading to this rightward shift in the head distribution. With increasing time, the head profile shifts further and further right until we establish the final steady state condition with the same gradient throughout the column. What we see then is at the top of the column, the gradient is constant through all time, but the pressure head and the hydraulic head is increasing through time. And this is exactly what we see when we add water at one rate to our soil body and then increase the flow rate. What's harder to see is that at the base of the column, while the pressure head and hydraulic head are staying the same due to the boundary condition that's applied, the gradient is increasing with time. So the flow rate is increasing from 0 to the final steady state flow rate. So what would we see if we plotted the flow into and out of the column as a function of time? At the top boundary it's fairly simple. It's the initial inflow rate until we change it to the new inflow rate. At the bottom it's a little bit more complicated. Remember, there's a time at which the bottom of the column hasn't felt any change from the change in the top boundary, so that outward flux would remain the same, and then it would slowly transition up to the final flux. The point at which the inflow and the outflow are equal is the time at which we reach steady state, and the area between those two curves has units of length and is the length of change of storage of water that has occurred through the transient period.